Hello! In our last video, we figured out that because astronauts on the space station are so close to Earth, gravity is pulling on them almost as strong as it is pulling on us here on Earth. So how do they stay up? Why doesn't the space station just fall down? Well, the answer is centripetal force. Take, for example, this bucket of water. I'm going to try to spin it without hitting the ceiling, but as you can see, the water in the bucket has defied gravity and not fallen to Earth. Don't believe there's water in here? Yes, there's water. And it's a good thing it didn't spill because that's pretty dirty water. I just got it outside. But anyway, that was in the garden. So, the same thing's going on with the space station. The space station is orbiting Earth. All our satellites are orbiting Earth. The moon is orbiting Earth. And it's a good thing too, because if the moon was just sitting there, it would fall on us. Because space isn't just some sticky substance where every time we launch something into space, it just sticks there like a spitball in the ceiling. Space, there's nothing up there to actually hold anything up. The only thing that holds it up is that centripetal force from whipping around the planet at considerable speed. Now, how fast is an object going if it's going to be held up there? So, centripetal force is equal to the mass of the object. Obviously, it takes more force to whip a heavier object around than a light one, times the tangential velocity squared. If you're going into a turn really fast, you need more traction to maintain control than if you're taking that turn really slow. That's why I was like, slow down, you're going into a turn. Why? Because you know you're going to need more force to make that turn. Over the radius of the turn. Tight turns, where r is small, require more friction if you're making that turn. And if you don't have enough friction, well, then you got to reduce that velocity. So we're going to simply, we're going to try to get velocity by itself. We're going to multiply r over m, and we'll cancel that, and then we'll take the whole square root of both sides. And basically, when you're done with the whole damn thing, you're going to end up with this. The tangential velocity, sorry, not even squared, sorry. The tangential velocity is equal to the square root of centripetal force times the radius over the mass. So let's start calculating here. So we're going to use our same astronaut before in order to find out how fast you have to be going to not fall out of space. So we're going to use the same astronaut before. We have found if he's up where the space station is, that our 102 kilogram astronaut has a weight or has gravity pulling on him with 894 newtons. We discovered that if you add the 370 kilometers to the Earth's radius, that you were out there a distance of 6.741 times 10 to the 6 meters. It's about 6,700 kilometers, which is 6.741 meters times 10 to the 6 meters. And of course, the mass of the astronaut is still 102 kilograms. And it's math now, okay? I didn't put these in scientific notation. I'm actually going to take this and divide it by 102 first because, you know, it's just easier. You can do it any way you want. You can just put it in your calculator. I just find it easier to kind of think about it. So, 8.94 divided by 102, I get 8.766 times our distance from the center of the Earth, 6. Well, it's still the same, 6.74. Why am I looking down there? It has not changed. And multiply that out. The tangential velocity. Multiply these together, and we get 59. 8.7 times 6.7 is 59. Times 10 to the 6th. That hasn't changed because there's no other thing to multiply by. And that's, of course, the square root. If I take the square root, the tangential velocity, square root of 59.09 is 7.687. So what times itself makes 10.6? It's 10.3. And so there is our answer. Now, one thing to think about here is how much of that? Well, 10 to the third. We just simply move this decimal point over 1, 2, 3 places, and we get 7,300 meters per second. And if you want to convert that, well, first we can convert it to kilometers, move the decimal point right back to where it was before. So that makes 7.6 kilometers per second. Now, your car probably doesn't give you your speed in kilometers per second. That's pretty darn fast. In case you're wondering what that is in kilometers an hour, just simply multiply that by 3,600 because there's 3,600 seconds an hour, 60 seconds in a minute, 60 minutes in an hour, 60 times 60 is 3,600. And what you end up with is, what did I get? 27,700 kilometers per hour. That is really fast. I mean, at that speed, you're basically going around the Earth in a little over an hour. Well, about 90 minutes. So you got to be going pretty fast. And that's why the space station orbits. That's why if you're going to the space station and you miss your launch window, you got to wait a while for the space station to come back so you can reach it again. So, but yeah, if you weren't going that fast, gravity would take over and you would fall. So, now you know how fast you got to go to keep from falling back to the Earth. And I hope this has been helpful. Bye-bye. Wait, can everybody see it okay? 27,700 kilometers per hour. If you can't, you can zoom in on your screen. Bye-bye.